talk about exponential growth and decay functions. Exponential growth functions are functions where the graph grows really, really fast. That's why it's called exponential growth. Decay functions are when the graph decreases really, really quickly. Decay functions. Now, something that's new with exponential growth and decay functions that we haven't run into before is that both exponential growth and decay functions have what's called an asymptote. An asymptote in this case is going to be a horizontal line that the exponential growth or decay function gets closer and closer to without ever actually touching it. So for the parent functions of all exponential growth and decay functions, the asymptote is the line y equals 0. And when we talk about transformations, we'll talk about what kind of transformation is going to change where the asymptote of the graph is. So because it's a horizontal line, moving the graph up or down is going to change where that asymptote is. But for the parent function, it's always going to be the x-axis, or y equals 0. So let's graph our first function. The first thing we need to do before we start graphing is to decide if this is going to be an exponential growth or an exponential decay function. To do that, we look at the base. So the base of this function is 1/2. That's what's being raised to the exponent of x. When the base is less than 1, when it's between 0 and 1, it's an exponential decay function. So this is a decay function. If that base was bigger than 1, it would be a growth function. And I should have mentioned previously, we call these exponential growth or decay functions because x, or the variable, is in the exponent. That's what makes it an exponential function, whether it's growth or decay. And then again, to tell if it's growth or decay, you look at the base. If the base is bigger than 1, it's growth. If it's between 0 and 1, it's decay. So when I make my XY chart, I like to plug in the numbers -2, -1, 0, 1, and 2. So first one, plugging in -2. When I plug in -2, or 1/2 to the negative second power, if you have trouble with negative exponents, try 1/2 to the positive second power first. That would be 1/2 times 1/2, which is 1/4. So because 1/2 to the positive 2 power is 1/4, 1/2 to the negative 2 power is the reciprocal of that, or 4. Remember, negative exponents create reciprocal answers. So 1/2 to the negative first power is going to be the reciprocal of 1/2 to the positive first power. 1/2 to the first power is 1/2. 1/2 to the negative first power then would be the reciprocal of that, or 2. And anytime we raise something to the 0 power, that answer is 1. So we have all of the points we're starting off with. We've got -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. And then if I would have kept going and raised that to the third power, 1/2 to the third power is 1/8. Fourth power is 1/16. Fifth power is 1/32, 1/64, 1/128. And as you can see, we're just going to keep getting closer and closer to 0 without ever actually touching it. My asymptote is at y equals 0. And if it's helpful, you can always draw in that asymptote before you get started. So my graph is going to get closer and closer to that. We can see that it's a decay function because it's going down, but it's never going to hit that asymptote. It's never going to cross it. So the domain for all exponential growth and decay functions is all real numbers. You can plug in any number for x that you want. But the range is always going to be limited based on where your asymptote is. So because our asymptote is here, all of our points are above that line. So all of my y values are bigger than 0. So transformations are the same idea for all functions, whether it's linear, absolute value, quadratic, cubic, square root functions. It's the same. So for exponential functions, if we're adding or subtracting to the x value, that's what moves the function right or left. So subtracting to the x is right, adding to the x is left. If we're adding or subtracting outside of the exponential part, that's going to move it up or down. Negatives create reflections, and then when we're multiplying either the function or the x by number, those are your horizontal and vertical stretches and shrinks. So what changes the asymptote for these exponential functions is the vertical translations. If we move the function up or down, that changes where your asymptote is, because the asymptote will also be moved either up or down. Let's try another graph. So I'm going to start by making my XY chart while we talk about whether this is a growth or decay function. So we know it's exponential because the x is in the exponent. And this particular problem is going to be a growth function because the base is 4. What's being raised to the x exponent is 4, and that's bigger than 1. So this is going to be a growth function. We are not moving the graph up or down, which means my asymptote is going to remain here at the x-axis. And again, I like to just plug in some basic negative and positive numbers into my XY chart. So 1/2 times 4 to the negative second power. Make sure you're careful to use order of operations on all these problems. So you always do the exponent first, 4 to the negative second power first, and then multiply that by 1/2. And if you have trouble knowing what 4 to the negative second power is, do 4 squared first. 4 squared is 16, so that's 1/2 times 16, or 8. So if 4 squared is 16, 4 to the negative second power is 1/16. So this is 1/2 times 1/16, or 1/32. When we plug in -1, I'm going to change colors. We have 1/2 times 4 to the negative first power. 4 to the first power is 4, so 4 to the negative first power is 1/4. I'll go ahead and jump down here and do 1 since we talked about that. 4 to the first power is 4. 1/2 times 4 is 2. And then 0 is the nice easy one. Anything to the 0 power is 1. So 4 to the 0 power is 1, but I still have to multiply that by 1/2. When we graph all those points, let's see, we have -2, 1/32. That's really close to 0. -1, 1/8, also really close to 0. 0, 1/2. 1, 2, 2, 8. See, we're growing really fast. And these are just going to keep getting closer and closer to 0 because that's where our asymptote is. This, as you can see, is an exponential growth function because it goes up from left to right. If we want to talk about the domain, remember domain for all exponential functions is all real numbers. And your range, because all of the points are above the x-axis, all of our y values are greater than 0. All right, another exponential function. This is another growth function because the base is 2. This one has lots of transformations happening, so let's talk about each one of those. The 4 is going to be a vertical stretch that makes it grow just a little bit faster. The -1 up with the x, that moves the graph to the right 1, and the -3 moves the graph down 3. So since asymptotes are normally at y equals 0 at the x-axis, if we're moving the graph down 3, now my asymptote is going to be down here at -3. And if I forgot to mention, this is exponential growth because our base is 2, and that's bigger than 1. And again, we can go ahead and plug in all of our normal points, -2, -1, 0, 1, and 2. Sometimes, though, if we're moving the graph to the right or to the left, I plug in slightly different numbers. Like if we're going to move this graph to the right one, I'm going to move all of the normal points I plug in to the right one. And the reason why I do that, this is just a personal preference thing. You can plug in any numbers you want into the XY chart because remember, our domain is all real numbers. So you can plug in anything you want. But just a personal preference, I like the middle number I plug in. When I plug in a 1, I get an exponent of 0. I like that middle number to give me an exponent of 0. Kind of like a baseline. So if my exponent is 0, 1 minus 1 is a 0. So I have 4 times 2 to the 0 power. Remember, order of operations matter. So we do 2 to the 0 power first, which is 1. Then multiply that by 4 and then subtract the 3. Now let's go ahead and hop all the way back up here to the -1. So when I plug in a -1, my exponent is going to be -1 minus 1, which is -2. So I have 4. 2 to the -2nd power is 1/4. 4 times 1/4 is 1, minus 3 is -2. If I plug in 0, I get 2 to the -1st power, which I know is 1/2. So this becomes 4 times 1/2, or 2 minus 3. When I plug in 2, I get 4 times 2 squared, or 4 times 4 minus 3. This one's probably going to be way too big for my graph then. 4, I'll change colors to make it look all symmetrical. 4 times 2, oh, I messed that up. Let's go back here. This is not 4 times 2 to the 2nd power. Because when I plug in a 2 up here, 2 minus 1 is 1. So that becomes 2 to the 1st power. So 4 times 2 minus 3 is 5. When I plug in 3, my exponent then becomes 3 minus 1, or 2. So 4 times 2 squared, which is 4, minus 3 is 13. Clearly, we have to be careful with these so we don't make some silly errors. All right, and when I go to graph all of these, I've got -1, -2, 0, -1. I already graphed 1, 1. We've got 2, 5, and 3, 13 is going to be off my graph, but I know it's going to be up there. We already knew that my asymptote was going to be -3 by looking at the transformation, so my range is all of those y values are greater than -3. All right, one more graph model. This is exponential decay because the base is less than 1. This function is being moved down 4, which means my asymptote is going to be down here at -4 instead of at 0. And it's being moved to the left 1, so personal preference thing, I'm going to move all of the points I normally plug in to the left 1, so that in the middle, when I plug in a -1 up here into the exponent, I get an exponent of 0 because -1 plus 1 is 0. I just like that middle one to give me an exponent of 0. So that would be 2 times 1. 1/3 to the 0 power is 1 minus 4. 2 minus 4 is -2 to get us started. -1, -2. All right, when we plug in -3, we get an exponent of -2. When I plug in -2, I get an exponent of -1. When I plug in 0, I get an exponent of 1. And when I plug in 1, I get an exponent of 2. And let's go through these. So 1/3 to the -2nd power, that's 9. So 2 times 9 minus 4 is 14. 2 times 3 minus 4 is 2. Down here, 2 times 1/3 is 2/3 minus 4 is -3 1/3. And down here, 2 times 1/9 is 2/9 minus 4 is -3 7/9. So you can see we're getting really close to -4 without ever touching it. So -3/14 is going to be way up here. -2, 2. -1, -2 we already had. 0, -3 1/3, and 1, -3 7/9. So domain, all real numbers. Range, all those y values are greater than -4, but it's a decay function because from left to right, it's going down. Let's briefly talk about exponential growth and decay models in general. So this one on the left is an exponential growth model because if we add something to a 1, then the base is going to be bigger than 1 because we're adding something to 1. This one over here is decay. It's not labeled, but that's a decay function because we're subtracting something from 1. And so that's going to be, that number, that base is going to be less than 1. So where we apply these is anytime something is going to grow or decay and model something exponentially. Usually it's in reference to time. The A stands for the initial amount. The R is the percent increase or decrease. That's a rate. And T stands for time, usually in years. So if we say the value of a car, Y, can be approximated by this model, where T is the number of years since the car was new. So let's talk about the different things what this means. So 0.85, that's less than 1. That tells me that this is a decay model. Or in other words, the car is losing money. The value of the car is going down each year. The percent decrease, how much it's going down each year, is how far away this number is from 1. So 0.85 or 85% is 15% away from 1. So this car is decreasing in value at 15% each year. The initial value of the car is 25, and it says it's in thousands of dollars. So that means the initial value of the car was $25,000. And then what we can do with this question is we can ask a follow-up question like, if it was initially worth $25,000, how much is the car going to be worth after 3 years? And so if I was to ask a question like that, we would simply plug in a 3 for T. And you would need to do the exponent first. So we're going to take 0.85 to the power of 3 first. And then we're going to multiply that by 25. And I'm getting about 15.35. And remember, this is in thousands of dollars. So in thousands of dollars, we would multiply by 1,000 to get about $15,350 would be the value of the car after 3 years. So that's how you would apply that. Let's look at another way we use this model. So here's another one where it wants us to write an exponential growth model because it says that the population is growing, it's increasing by 1.18% each year. So the first thing we need to do, this is given to us in a percentage, but the rate is always going to be a decimal. So we need to convert 1.18% to a rate, and that would be 0.0118. So that's our rate. Our initial amount, or we're starting in 2000, so the initial amount as of 2000 is 6.09 billion. And so let's go ahead and start our model then. We've got y equals the initial amount, 6.09. What goes in the parentheses, our base is going to be bigger than 1 because it's an exponential growth model. So we take 1 plus the rate, and we're going to raise that to the power of t. And then you can go ahead and add the 1 with that rate. And it says estimate the world population in 2005. Well, if we're saying this all started in the year 2000, 2005 means that t equals 5. So to solve for that, I'm going to plug in 5 for t. Order of operations says we need to raise the 1.0118 to the 5th power first, and then we multiply that by the 6.09, and I'm getting about 6.46, which would be in billions of people.